All right, so I'm going to record and, oops, I'm going to call up a PowerPoint, all right, and to help us with this, all right? Okay, so electromagnetism. I have to do that too. So electromagnetism. And so Hans Christian Ørsted, who was Danish, discovered this. He discovered that a current carrying wire affected a compass needle, all right? So what that means is, you know, remember how only a magnet can affect another magnet? Okay. What that means is a current carrying wire was a magnet. Okay. If you pass current through a wire, as if by magic, a magnetic field appears around the wire. And he did some experiment, and he found, and we call this an electromagnet, a magnet produced by electricity. All right. And the field lines, well, you don't have to draw this, but the field lines, he did some experimenting, and they formed concentric circles around the wire. Okay, well, you can attempt to draw that if you wish. They form concentric circles around the wire. All right, and yeah, he discovered this basically by accident. Okay, and I'd like to actually show you a recreation of this. I can't do it in front of you because I don't have the stuff. So I cheated a little bit. I'm going to go to YouTube for this. Okay. All right. So I'm going to show you a video of this.
Having a wire that goes through a piece of cardboard here. And I've got it surrounded by little tiny compasses. They're all pointing generally this direction. I'm going to run current through the wire that will be coming up the wire this way from underneath.
Can you tilt the camera up a little bit?
So based on the right-hand rule, there should be a magnetic field around this wire. In which direction? Let's find out.
Never mind about that right-hand rule.
I'm going to clip this on.
Watch what happens with compass needles.
Now. So it looks like all of the arrows are tending to go around in a counterclockwise fashion from this perspective. Turn the current back off. I'm going to reverse the current.
So the magnetic field was on when the electricity was on, and it was off when it's off. Okay, so it magically comes into being when you run current through it. When you take the current off, it just collapses, disappears.
Run it the other direction. So in this case, the current will be flowing down the wire through the cardboard. And let's see what direction the field is there. Now they all seem to be pointing in a clockwise fashion around the wire. The farther I get from the wire, the weaker the field seems to get.
Yeah, I'm not going to get into that. There's that culminates in an equation, and I'm not going to worry about that equation right now. So by passing current up through the wire, okay, the field went around the wire in a counterclockwise fashion. When you reverse the direction of the current, the field lines now, well, the field lines then went clockwise, reversed. Leave it. Oh, yeah, sure, go ahead. Yeah, it's kind of a draft. All right, so yeah, so they reverse direction, okay? And so, so you can show this, okay? So it's all I'm going to do with that video for now. So I'm going to exit that and get back into my PowerPoint. Okay. Is that camera okay? Those at home? Let me know if it isn't. All right. Okay, I'm going to get the room light.
It's good.
All right, good. Okay, now we need a way to remember this. We need a way to remember, okay, if the current goes up, you know, if the current goes up, the field goes this way, if the current goes down, the field goes the other way. How are we going to remember that? Well, somebody, and I don't know who, invented this notion of a right-hand rule. Okay, let me show you how it works. So if you have a current carrying wire, I was trying to move this over. Didn't work. Let me point this way. If it's run up through the wire, it goes around. And also, it's hard to draw. It's hard to draw circles around a wire. That's a three-dimensional thing on a two-dimensional surface. You know, how do we do that? Well, there's a way to do that. But before I do that, if the current is going up in the wire, okay, then it goes this way. If the current is going the other way, then the magnetic field does this. How do we remember that? Well, somebody invented a right-hand rule. Take your right hand and pretend your pencil. Put your pencil in your right hand. Okay, pretend your pencil is the wire and orient it so that your thumb is pointing up towards the ceiling. Now, look down on your pencil. Which way do your fingers go around that pencil? I say in a counterclockwise direction. You see it? Look at your fingers. They curl in a counterclockwise direction. All right? Okay, now, let's say we pass current down. Now I gotta do this. Now, contort your body. Now, which way do your fingers go around the pencil? They go clockwise, all right? So I don't know who invented it, but whoever did us a favor because it's an easy way to remember how the magnetic field goes around a wire. You put your thumb in the direction. So the right-hand rule for this, I actually have this. Thumb of the right hand points in the direction of the current, and then the fingers wrap around the wire in the direction of the magnetic field. That's the right-hand rule for a current-carrying wire. Okay? I don't know who invented it, but whoever did us a favor. It's an easy way to remember. Now, how do I draw this? You know, it's really hard to draw a 3D thing, three-dimensional thing on a two-dimensional surface. So instead of drawing circles, which is very confusing, you know, which of these lines is in front of the wire? Is it this one or is it this one? Is it this one or is it this one? Which one's in front of the wire? It's very confusing. So somebody invented a notation to take care of this, okay? And for this wire, with current going up, the field is going into the paper on the right side, coming out of the paper. Where's my, I do it, oh. Going into the paper on the right side, coming out of the paper or out of the board on the left side. How do we notate this? Well, you've invented, somebody did, I don't know who, invented this notation that looks like this. If you, oh, by the way, oh, okay. It looks like this, an X with a circle around it. An X with a circle around it is like you're looking at the back of an arrow as it's going away from you. All you see are the fletchings on the wire, okay? This symbol means out of paper. Oh, sorry, that's wrong. Into the paper. Into the paper or into the board, okay? It's an X with a circle around it. It's like you're looking at the back of an arrow, okay? On the other side of the wire, the field is coming out of the paper. The symbology for this is a dot with a circle around it. So like you're looking at the tip of an arrow as it's coming towards you. So this symbology means out of paper or out of the board. Okay. And then one other thing, we label this capital B. For one reason or another that I don't know, we use B to symbolize magnetic fields. Why? I don't know, but that's what they use. So the symbology for this, the magnetic field for this goes into the paper on the right side, comes out of the paper on the left side. Okay? All right, that's how to, it's an easy way to draw a 3D thing on a 2D surface. Okay? All right? Okay. Please, in your notebook paper somewhere, let me erase this. Cover this up. Can't get it. Practice this right-hand rule stuff. So, draw horizontal line. This is going to represent a wire. Okay? And we're going to pass current in from right to left. Like that. And what I want you to do is to indicate the direction of the magnetic field above the wire and below the wire. Okay? So you're going to draw one of these symbols above the wire, like right around here. And then you're going to put a symbol below the wire, right around here. Use the right-hand rule to indicate the direction of the magnetic field around that wire. Use the right-hand rule. Talk it over with somebody. You think you know. Confer with the classmate. Compare your answers. Okay, who's confident in their answer? Go ahead, Lee. What do you think? Did I interpret your response correctly? What do you think? What do you think, folks? You agree with that? Right-hand rule. Into the board above. Thumb's going to the left, right? In, right in. Yeah, that's right. So thumb to the left, into the paper, out of the paper. I agree. Yeah. Label it B. Put a symbol by one of them. Doesn't matter which one. Label it B for magnetic field. Yes. Those of you at home, you okay with that? All right. Yeah. Okay, so that's just an easy way for us to remember. Well, I have all that in the PowerPoint, but I'm just going to blow right past it. Yeah. Okay, good. All right. Now, having a straight wire is kind of interesting, but we can make it more interesting if we take that wire and make it into a loop. All right? Let's make it into a loop of wire. All right? So instead of this, let's make it a little bit more interesting. Let's have a loop of wire. So I have something like this. Okay? Something like that. I'm sorry, what? Well, I haven't told you yet. Well, let's pass current in. I'll get into that. Let's pass current in like that. Okay? So the current is going to go around the loop like this. Now let's examine what's going to happen at various parts of the wire. For example, what about down at the bottom here when the current is like this? According to the right-hand rule, what is the orientation of the field over here? I know, thumbs over there. I say it goes into the board, below the wire, coming out of the board, and the top of the wire. Would you agree? Yeah? Okay, so it's going to go into the board there, out of the board there. Okay. Then let's go over here. The current's doing this. Now, what about by the right-hand rule? Thumbs pointing like that. Into the board to the right, coming out of the board to the left. Would you agree? Okay. So into the board, into the board there, out of the board there. All right, what about on top? Up here, current's going this way. Okay, according to the right-hand rule, into the board at the top, out of the board at the bottom. So into the board at the top, out of the board at the bottom. Yes? Okay. Notice that on the inside of the loop, it's always coming out. The outside loop is always going in. Okay, they actually form concentric circles, but we're not going to draw those because it's too confusing. We're just going to draw it like that. All right? Okay so far? Okay. All right. And I had this again in the PowerPoint. I'm just advancing to it. Okay. That's a loop. So if I pass current in, you know, this direction, that's where the magnetic field would be going like that, like that. All right, well, that's kind of interesting. But it's even more interesting if we take a whole series of loops and we make a coil out of it. Like this. Like this. Which I made by just wrapping a wire around a beaker. Okay. Now we have a series of loops. Okay. And current's going to pass through each loop. And it's going to do this in each loop. All right. And it's going to create a magnetic field on the inside. Maybe. Should we see? Let's find out. Okay. I got a little setup to do. It's going to take me a few minutes. Got my charging cord because that's just kind of in the way. Like whole bunch of setup time for not a very long demonstration, but that's okay. So I want you to see. I also need something else. So I'm going to suspend. Actually, I'm going to get out of here. I'm going to escape out of PowerPoint so I have to get the photo booth. Again, this is a whole lot of setup for a rather short demo, but that's okay. So I'll do this. And this like this. Hope it doesn't fall off the table. Don't be bad. I have a little compass inside here. So this, I don't want that thing falling off the table either. So now, those at home are seeing the tabletop, and you're seeing the tabletop. And what I want to do is, first of all, light this whole thing up, because it's when I dim the room lights, it's going to be rather dim. I'm going to do that, like that. And put my flashlight on. Now, can you see the compass needle in there? Can you see the compass needle? Right there?
I can see it.
Okay, cool. All right, then you need a battery and some wires. All right, and oh, I forgot the battery. So I got a battery with wires here. And I'm going to connect the wire there and the wire there. And I'm going to pass current in the coil starting now. See the compass needle deflect? Okay. All right. Which way is the red end point? To the left. All right. Notice when I remove the electricity, the magnetic field collapses. It immediately goes to zero. This is an electromagnet. It's a magnet produced by electricity. On when the electricity is flowing, off when it isn't. So I can control, unlike a permanent magnet, I can control whether a magnetic field is present or not. All I have to do is turn on the electricity, and the magnetic field is produced as if by magic. Okay, notice the needle deflects clockwise, well, from actually counterclockwise, so that the red end point's left. What if I reverse the direction of the current? What's going to happen then? Let's reverse the direction of the current. Which way is it pointing now? Points the other way. Okay. So not only can I control whether the magnetic field is there or not, I can control its polarity. All right. Simply by passing electricity one way or the other. Okay. That is an electromagnet. It's the magnet produced by electricity. All right. Okay. Questions before I take this thing down? No? All right. You take this whole setup down. It's rather precarious. I'm going to some other stuff to show you. that off. Come on. Okay. These on. Get back to my PowerPoint. Here, no, that's the lab groups for your lab next time. Oh, there it is. So, come on, you can do it. So I did that. Okay. Now let's have a series of loops. Okay. I actually want to turn this off. I want this back yet. I actually don't need that all that much, but it's there. It's closer for you at home. So what I'm going to do now is I'm going to draw a coil. Now you don't have to draw this. It's all in Schoology. You want to draw a coil. I want to draw it like this. Okay, with the breaks in the wire indicating what's in the front, what's in the back. We draw it like this. Okay, and I'm going to have the battery go like this. So current is going to come out like this. Okay, current is going to come out like this. All right, it's going to go around the coil. It's going to go down in the back, up in the front. Down in the back, up in the front. Down in the back, up in the front. Down in the back, up in the front, and back to the battery. Okay? Now, in each coil, since it's going up in the front, for each coil, the magnetic field is generated. It's going to be the same. Now, check this out. Remember, look. Let's look at my previous loop. Okay? If the current is going in up like that, then the field came out of the paper when the current is going up. I'm just going to rotate this whole thing. Remember, this is coming out. If I rotate this so that this is in front of you, that field is going which way? Magnetic field, this magnetic field, which is like this, if I rotate the coil, which way is it going now? I say it's going to your left. Do you agree? So the magnetic field inside each of these coils, magnetic field in each one, it's going to the left. So that one's going to the left, and that one's going to the left, and that one's going to the left, and that one's going to the left. And then he merges like that. Okay? Then wraps itself around, goes right back in. Okay? So the field looks like this. Okay, now, if I had a bar magnet with a field line that did this, which pole of the magnet, what are the poles of the magnet? Which one's north and which one's south? Which one's north and which one's south? If I have a field line that looks like this. The left one is north and the right one is south. Field lines go from north to south? Yeah, they do. So this coil would act like a bar magnet that has a north pole on the left and a south pole on the right. Okay. So if I take this coil and I put it so that the current is going up in the front, down in the back, up in the front, down in the back, I'm going to have a north pole over here. Oh, look what happens. If I take my right hand and I put the coil in my hand such that my fingers go up in the front, which way is my thumb pointing? My thumb is pointing to the North Pole. Huh! Now we have a right-hand rule for coils. So if I put my right hand, if I curl my right hand around in the direction that the current flows, because my fingers can curl, then my thumb points to the North Pole of the coil. That's the right-hand rule for coils. Okay? All right? And I'm going to give you guys a moment to write that stuff down. Okay. That's the right-hand rule for coil. I just didn't want to just yank it out of the sky. I wanted to show you where it came from. Okay, so that's why I developed that. But that's an easy way to get the magnetic field around a coil. Okay, if you send current in such that it goes up in the front and down in the back, up in the front, down in the back, then you will get a north pole on the left side of the coil. Okay? Oops. No, that's right. I get a north pole on the left side of the coil. That is the right-hand rule for coils. Okay? Right? And we get what's called an electromagnet, which is super useful. You have lots of electromagnets in your home in various devices because it's advantageous. Sorry. Because it's advantageous to have a magnetic field when I want it and to get rid of it when I don't. And it's very simple to do. All you need to do is pass electricity through a wire. And as if by magic, the magnetic field will appear. And I can control the polarity. I can control which pole is north extremely easily. Okay. Fingers wrapped around the coil in the direction of current flow. Thumb points to the north pole of the coil. Okay, and we get what's called an electromagnet. All right. Here are another example of them. Okay. Here, if I orient it vertically, pass current in like this, wrapping my fingers around direction of current, my thumb points to the north pole of the coil. Okay. Okay, now, so I have myself an electromagnet here, but it isn't very strong. You know, it's really weak. How can I make a stronger electromagnet? There are three ways. Three ways to make a stronger electromagnet. Anybody want to guess one? More coils. Nice, because each coil adds to the magnetic field. That's one way. What's another way? More current. Nice, because the current generates a magnetic field. If I have a stronger current, I want to have a stronger field. Okay, those are two ways. The third way can be a little more difficult. People usually get this one. Go ahead. Actually, you would think that the size of the coil would make a difference, but it doesn't. It's a little bit counterintuitive, but it actually doesn't. Yeah. How tight the coils are together. Surprisingly, that doesn't seem to affect it either. Yeah, I can understand why you're guessing that because I would guess kind of the same thing. But surprisingly, it doesn't have that much effect. No. Yeah. Temperature? No. The temperature might affect the resistance of the wire, which might affect the current. So that might be wrapped up in this. No, it's a strange one. And I'm just going to give it to you. This one I'm just going to give you. Add a ferromagnetic.
Mr. Couches, can you let Kayla into the meet, please?
Oh, yes. Okay, thank you for notifying because I didn't know. Let's see, I'm gonna have to do this. Add a ferromagnetic core. You guys can write that down while I'm letting her into the meet. Thank you for letting me know. Adding a ferromagnetic core. Yeah, that's the one I want. How do I get back to the, oh, here it is. More coils, more current, and insert a ferromagnetic core. And why you guys are writing that down? Why does that work? Well, because a ferromagnetic core, such as this steel rod, I have a bunch of wires right around. Right now, there's the domains are random, right? But what happens to the domains in the steel rod when there's a magnetic field inside the coil that rests on? What happens to the domains? They all line up and it becomes a magnet. Yeah, and a much stronger magnet. Okay, so I'm going to connect this to the battery, which I put over here. Connect this to battery, okay? And when I have current flowing, now it's a much stronger electromagnet, okay? because now all the domains are lined up. What happens when I take the electricity away? And they're all gonna randomize again. Some residual stuff. Yeah, okay, so the domains randomize again, all right? So that's it. You have an electromagnet there, all right? Okay. Did you ever do this? Did you ever do that? Hopefully you did this in elementary school. You took a nail, wrapped a wire around it, connected it to a 9-volt battery, okay? Hopefully you did that. If you did, you made yourself a little electromagnet, okay? Why'd you use a nail? Why don't you use a pencil? Huh? Yeah, so it's made of iron, so it's ferromagnetic. Where'd my nail go? This has domains. Does this have domains? No. So these have domains to line up. Yeah. Why'd you use a 9-volt instead of a little wimpy old, D cell? Well, you want more voltage. More voltage, you get more current. Right? And you wrap it like 100 times. You have yourself a little electromagnet. If you don't have a magnetic screwdriver and you forgot to bring it in so I could magnetize it, you can make it. If you got a screw way down there and you can't get it, just wrap a bunch of wire on it, connect it to a 9-volt battery. Your screwdriver is an electromagnet. You pick up that little screw way down in there. Okay. All right. You can make yourself one. You need a battery. And that's an electromagnet. Now, they use them in junkyards too. For what? What do they use them in junkyards for? Mason, yeah? No? Huh? What? They pick up cars. Yeah, pick up cars. So that's a steel disc with a whole bunch of, I'll go get my car. Okay. I get my car. And I want to get the car into the car crusher, right? So I do that with this. It has to be a crane because cars are heavy. You have a heavy disc of iron, okay, steel, a whole bunch of wraps of turns of wire on it, okay? And then it's connected to an electric circuit. And when the junkyard operator wants to get the car from the ground to the car crusher, he just drops it on there, get the wires connected. Actually, I'll do this. Drops it on there. Oops. Okay. Turns on the power. Gee whiz. So hard. Turns on the power. Picks up power. What's going on here? Huh. Grab the insulation instead of the wire. So I pick up the car. Oh, finally worked. Yeah. Yay. Then I take it to the car crusher. How do I get it off? Turn it off. Turn it off. Simple. All right. Simple. Can I pick up aluminum cans that way? Can I pick up aluminum cans? No. Why not? Saving cans. We need my recycling container. Throw them out. You pick up a can. Can I pick up a car? I can pick up a car. Can I pick up a can? No. Why not? Yeah. They don't have things called, they start with a D. They don't have domains. Yeah. Aluminum's not ferromagnetic. So can't do it with cans. With cars. This wire's starting to get hot. Better take it out. Okay. So there you have it, electromagnets. Extremely useful thing. All right. Okay, next topic. Forces on current carrying wires. All right? Forces on current carrying wires. I'm going to spend about 15 minutes on this and then stop. Okay, let's say forces on current carrying wires. Let's say that you had I'm going to hide this for a while. Let's say that you had a horseshoe magnet and you had North Pole over there and the South Pole over here. You're looking edge on. You see this at home? You're looking edge on this thing. You got a wire hanging in the field. Like this. Okay. I pass current through the wire. And let's say that I pass current up like this. Pass current up in the wire. Okay? Now, this current is going to generate a magnetic field around the wire. According to the right-hand rule, what's that field going to look like? In on the right side, out on the left side. Would you agree? Okay. So I got in on the right side, out on the left side. This is field generated by the current. Okay? Field generated by the current. Now, I also have magnetic field lines from the bar magnet or from the horseshoe magnet, and they go from north to south. Field, B field from magnet. Well, the magnetic field from the magnet is going to interact with the magnetic field from the current. And they're either going to attract or repel each other. Okay? All right. I'm going to show you this over here. Those of you on this side of the room, it's real nice because it's right in front of you. Those of you on the other side of the room, it's going to be a little tougher. So I want to project it up on the screen. So that means I have to get out of the car. Get back in the photo booth. Which is oh dear. Okay, I got it back. Okay. So sorry. So you can see that right here, I have a wire that's hanging in the field around my very strong horseshoe magnet. And I'm going to pass current through the wire with this battery. Okay? Okay. Watch what happens when I connect the electricity. See the wire move? It moved out. Okay? I take the current off, and the wire collapses to where it was. Connected, it's pushed out. Remove it, just hangs it. Okay? Now, what happens if I reverse the direction of the current? What's going to happen now? Now, the wire gets pulled in. You see that? Okay? Wire gets pulled in. That. Okay. So when I pass current, there's a magnetic field generated around the wire that interacts with this magnetic field, and it either pushes a force results. A force that either pushes the wire out of the field or pulls it into the field. Okay? Okay. And how can I remember the direction of the force? Well, you guessed it. There's another right-hand rule. Okay? There's another right-hand rule for this. And let me describe what it is. So, first let me write stuff down. B field from magnet interacts with B field from current. From current. Okay? Force results. Force results. Direction found by the right-hand rule. Okay? Okay, here's the right-hand rule. Fingers go with the field, B field, north to south. Fingers, feel. Fingers, feel. Thumb. Your thumb points in direction of the current. Direction of current. I. Okay? Then your palm shows the direction of the force. Your palm shows the direction of. Okay? You have your right. Oh, extreme apologies to those of you at home. I forgot to move the computer. Very sorry about that. So here's where we are. Okay? So the B field from the magnet interacts with the B field from the current. Force results. The direction is found by a right-hand rule. Okay? So let's predict the force from this setup right here. Okay? Keep it on the screen so everybody can see it. Fingers north to south of my right hand. My thumb goes in the direction of the current, up. And my palm faces out of the board. So in this particular case, with my fingers north to south, okay, my thumb pointing up, my palm is facing out of the board. So the force out of page, out of the paper, out of page, out of board, whatever you want to call it. Okay, it comes out like that. All right. Okay, let's apply this over here and see if this stuff actually works. Now, I will tell you that in my very strong horseshoe magnet, the bracket here is the North Pole. So the North Pole is here, South Pole is here. And I did that on purpose so that I could have my right hand. And I'm going to pass current in that's going up, okay? And the positive terminal is the one in the corner. So I want to take that to the bottom of the, so I want to have that going like this, okay? So if I have fingers north to south and the current going up, the palm is facing towards you. So when I make the connection, the wire should move that way. And it does. Okay? Okay, now instead, let's have the current going down. Now my fingers still point this way, north to south, but now I pivot my thumb down. Which way is my palm face? Palm face is in. When I do that, we get, okay? So that's the right-hand rule for the force on a current carrying wire. Okay? Now you're saying, yeah, okay, fine. So what? Well, okay, let's have some fun with this. Let's alternate that way and 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 that way. I can get that wire going back and forth, which is kind of fun. All right, now let's do it really fast. If I could get that wire going, vibrating back and forth really fast. Oops. I'm sorry, those of you who can't see that. because you're on the other side of the room. Okay. Okay, I can get that thing. Let me do this again. Oh, I lost the other way. Oh. So I could go that way and then that way and then that way and then that, and that way and then that. If I could go really super fast, I could get that wire going. And there's only so fast that I can do it. But let's say I switch the direction of the current electronically. So it switch directions like 100 times every second, or 200 times every second, or 500 times every second. Then that wire would be going. Okay. Then let's say I connect something to the wire, like, I don't know, a piece of cardboard. And that piece of cardboard would go 200 times a second. Okay. And if I did that, I have one of these. This is how a speaker works. Now, a lot of people know the speakers have magnets in it, right? May not have known why. This is why, okay? Because embedded in the magnet of the speaker is a wire, or more specifically, a coil. So if you have a dead speaker, rip it apart, take it apart, see what it looks like. And a kid did this. Never forget her name, Jill Dean. Many years ago. She's probably married in probably mid-30s by now. But he went and took it apart. She gave it to me. And like this. Embedded in the magnetic field of the speaker is a coil of wire. You guys see that? Yeah. And by passing current one way, pushes the cone out. Passing the current the other way, pulls the cone in. Does that many, many, many times every second. Every time it goes forward, what does it do to the air? Compresses it. Guess what we have then? We have a sound wave. Yeah, that's how speakers work. Okay, it's a force on a current carrying wire that's embedded in a magnetic field. It's this. This much more fancy. Okay, so that's a principle of operation of a speaker, among other things. There's lots of other applications of this, but this is probably the one that touches your lives the most, at least right now. Okay, all right. So that works. Kind of cool, isn't it? All right. Now, let's see. Getting back to this, just finishing this up. Getting back to this. I think just about done. Okay. I have all this stuff in the PowerPoint in case you didn't get stuff written down. Okay. I have all this stuff in here. All right. And I showed the right-hand rule. Okay. The direction of the force in this case would be out of paper as indicated by that. So it's all there for you want. And then that's the application. All right. Okay. I'm going to stop here. All right. And what I'd like you to do for the rest of the period is to, you now, dig out, please, 20 questions about magnetism. Dig that out, please. We have almost 15 minutes. You now have all the information you need to answer all of the questions. I would like to clarify number 20, please. Number 20, because it can be confusing. Okay. Number 20, as of right now, reads, what is the right-hand rule for a current carrying wire in a magnetic field? I should have worded that more clearly. Would you please insert the words, what is the right-hand rule? What is the right-hand rule for the force on a current carrying wire in a magnetic field? What is the right-hand rule for the force on a current carrying wire in a magnetic field? Okay. Okay, you have the rest of the time to finish this. Tomorrow, I'm going to collect these 20 questions about magnetism and your magnetism lab. So you have 13 minutes. Finalize all your answers to that. Okay, you should have you should have all the information you need to answer those questions. Okay, tomorrow I'm going to collect collaborative test corrections. If you want to do those, you may, and we'll have some time tomorrow to work on that. I believe I'll take those by the end of the week. And those of you who gave that to me in a written copy, I'm going to give those back to you now. And collaborations are due by the end of the week. Okay. So that's okay. So the rest of the time is yours. Feel free to work together. Feel free to ask me questions. You finish your worksheet?
Yes.
I'll take it. And your lab. Yeah, if you have them finished, you say, Mr. Dodge, can I just turn them in so I don't lose them? Yeah, put them in the stock style. Get started on correcting. Ronan. He got there first when he gets back. Okay. And then there's a sign up sheet.
Thank you.
Okay. Those of you at home, you can submit the 20 questions about magnetism and the magnetism lab. Submit to Schoology by the end of tomorrow. Submit to Schoology by the end of tomorrow. I hope the demonstrations, you were able to see the demonstrations. Oops. Oh yeah, I'm going to stop recording. I need to record it.